Guys, we'll get started in a little bit. Okay. Let's see. I wanted, all right. Yep. We'll get started. So our goal is to go over the test and maybe skip a few because I noticed there is an electrochemistry one that we couldn't do. So we'll do as much as we can, and we'll review acid and base and everything. So so in case you guys can't come in person, we also have online. So our goal is this. Right now we are in February, so let's say February 13th. This is our first. We're going to review AP free response. So every week we're going to do a free response or multiple choice, kind of alternate. That's too much for 1 week. So if you look at the 13th, we have 13th, 1, 20th, 2, 3. So 3 weeks in February, 4, 5, 6, 7. Then we have 8, 9, 10, 11. We have 11 more weeks. That's it. And then AP is the first week of May. Crazy. So 11 weeks. So that's why I want to start testing early, even though we haven't completely finished the curriculum. So do as much as we can, and then we can come back and review like that. So you'll get used to the test questions. And then once you get used to the test question, hopefully you'll feel that chemistry is not so bad. But the foundations, like what you guys are going into, equilibrium, acid and base, those are very important foundations. Okay, so I might have to go over equilibrium with you guys, review again, but we'll see how you guys do. So let's take a look at, so the whiteboard. So I'll post the whiteboard here after we're done as usual. And I also will post the video. So the class is recording. So I'll do the recording. So I think it's easier. Sometimes you can just watch the video again, just download the video. So it's going to be posted on the Google Classroom. On the Google Classroom, I'm going to ask the office to upload the class video. So you can fast forward to the part that you need to rehear again in case the note is not as clear. So we're going to start doing that because there's test review. Okay. So that means we're going to have only about 11 weeks and the spring break to prepare for the test. Okay. So it's not a lot of time. So we wanted to get to it as soon as possible. Alrighty. And so with that said, let's look at our test this week. And all the free response questions are released. So I just want you guys to know. Okay, so the format of the test, if you forgot, the free response is 7 free response. The first 3 questions are long, and they are 10 points each. So that's 30 points already. Now the last 4 questions, question 4, 5, 6, 7, they're only 4 points each. So that will be only 16. 4 times 4 is 16. The first 3 is like 30, and the last 4 is 16 points. So the first 3 is like more than twice the last 4 questions. And they give you a little bit of time. So the strategy here is not to pace yourself. A lot of people pace yourself. They do question number 1 and say, oh, I got this, I'll take my time. No, you don't want to pace yourself. You want to do as fast as you can on questions that you know and you're confident in. So if you saved for that question 5 or 6 minutes, you get to use those 5, 6 minutes to think about more difficult questions. So you don't want to pace yourself. You want to do as fast as you can on the ones that you know what to do. Save those time for question that's more difficult, more engaging. And you never want to do this because AP Chem, you look at the first question, they break it down into A, B, C, and there's like, they're not even done. They're like D, E, F. Sometimes you have E1, E2, right? So you don't want to get stuck on, for example, E2. And then you're so stubborn that you spend like 10 minutes on E2. Then you're going to get screwed over the test. It's just maybe just 1 point. And you may not get it right anyway. So just move on. Leave enough space, ample spaces to come back to, because it's going to be handwritten on the AP packet. And then you just move on to the next question and then come back when you have time. So they will break apart the test into so many different parts. So make sure you don't fall into that mistake of spending too much time on one part of the question for that one little lousy point, and you delay yourself for everything else. Okay, you will be struggle for time, but in the beginning. Later on, chemistry is so easy to finish. It doesn't really take a lot of time. Okay, but you have to memorize certain foundation. That's the thing about chem. Okay, So this is the first question. So let's take a look at that. So usually you can kind of tell what kind of question it is. This one has delta H, so heat of formation, right? Heat of the reaction, delta H questions, right? So I gave you guys 5 ways to find delta H. There's also a little bit of redox. They ask you for oxidation number, redox reaction, and this is thermocalorimeter. If the reaction causes the environment temperature to go from 20, you can see 20 here, to about 30 something, then the reaction is what? It's exothermic because it's releasing heat. That's why the environment heats up. So this is exo. Do not confuse this graph. I'm going to write on the screen some of the time. So don't confuse this graph, temperature versus time, with H versus time. H versus time, exo looks like this. This is exo. But if you are monitoring the temperature versus time, this is exo, right? Because it will heat up. Okay, so don't confuse those two. Okay, so that's one thing. So you can see this is stoichiometry and then calorimetry, so heat, yeah, limiting. So that's it. First question. They'll try to squeeze in as many chapters into the first 3 questions as possible. And the first 3 questions, you have to use calculator. Okay, this calculator, you can use calculator for the full response. For multiple choice, there is no calculator. You cannot use calculator, and there's 60 multiple choice. Okay, so we'll look at multiple choice later. For first few weeks, we're going to focus on free response because that's the best way to understand. And AP also loves those diagram questions. You got to draw particle level representation. I just call them diagram. Yeah, so you got to draw certain diagram, but not hard at all. Okay, so this is actually stoichiometry, something like that. And then I see thermodynamics, delta G, delta H, delta S questions, right? So thermodynamics, okay. And then, so they try to mix them together, and then they talk about pressure, gases, right? Gas equilibrium, gases. And then this is about Lewis structure. You got to be able to draw the Lewis structure. And then a little bit on here is the titration stuff. So, so we have that. Okay, so they try to bundle everything together. And number 3, another long question. This is talk about atomic radii. Intermolecular forces. I see redox reactions, stoichiometry, titration here. A little bit on experiment setup, and then just percent by mass and calculating moles of the product, stuff like that. So those are the 3 most difficult questions. Yeah. And then again, question 4, 5, 6, 7. There's only 4 points each. They're much shorter. So they're usually part A or B. That's it. Maybe part C. And then and this can be intermolecular force. Can be sometimes there are calculations. You never know. Yeah. So I just want you to be aware, and this is acid and base as well. Okay, so with that in mind, let's just start going over the test because I only have 1 screen, so I have to go between screens. So let's take a look at that. This is from 2018. All the free responses released. You get some you get some equation, 2 pages of equations that if you have to use it. All right, so let's look at the first question, yeah? So the first question is talking about right here. You're given this equation, so don't get bogged down by looking at the equation. Sometimes you spend so much time reading the equation, and it's just a waste of time. So the question says, they want to determine the delta H for the reaction, okay? And they tell you this is redox already, okay? So if this is redox, you have to be able to find the oxidation number very quickly, yeah? So the oxidation numbers is very easy to tell. For example, it's most likely the sulfur here because sodium is always 1+. So it's 1+, left and right, doesn't matter, right? So it's going to be focused on sulfur and maybe on chlorine because oxygen is usually 2-. So right away, I know these are the 2 probably that they need to find, okay? So you just write down the oxidation number. So if you're good with the oxidation number, you should be able to do, for example, this one. What is the oxidation number for chlorine in here? So the easiest way to do oxidation number is to separate them. So if I separate this into Na plus and then OCl minus is hypochlorite. You don't need to know what it's called. But from here, you can tell the oxidation number for Cl must be 1+ because oxygen is 2-. So chlorine in OCl minus is 1+. And that is the answer for part A. Okay. Does that make sense? Okay, so for ionic compound, just break it apart. Oxygen is always 2- except in hydrogen peroxide, in which oxygen is only 1-. Otherwise, oxygen is 2-. chlorine is not as electronegative, has to be 1 plus here. Now, if you look at the chlorine in sodium chloride, it's going to be 1 minus because sodium is 1 plus, CO is 1 minus, so it's 1 minus. So what happens to this? So oxidation number change, and this will be a reduction because oxidation number goes down. You gain electron. That is why oxidation number went down to 1 minus. Every time oxidation number goes down, you are reduction. If oxidation number becomes larger, like 1 to 2 to 3, that's oxidation, yeah? So if this is reduced, what do we call this? This is called the oxidizing agents, don't forget. They can also ask you to identify the oxidizing agent. Oxidizing agent is reduced, okay? So if you look at sulfur, it must be the other way. So sulfur in this case, we can look at oxidation number. So how do I find oxidation number for sulfur here, right? We're not asked to do that, but you should be able to do it also, right? So again, now you break it apart. So S2O3, 2 minus, right? Because sodium is 1 plus each. And oxygen, we know, is 2 minus each. So sulfur here must be 4 plus. Not 4 plus, I'm sorry. Must be 2 plus, right? So each sulfur is 2 plus. There's 2 of them, makes 4 plus. Oxygen is 6 minus altogether. That's how you add up to 2 minus. So sulfur went from 2 plus here to 4 plus in SO4. SO4, sorry, SO4 is 6 plus, I'm sorry, yeah? So to 6 plus in SO4, right? So in this case, sulfur is oxidized, okay? Sulfur is oxidized as it went from 2 to 6, that's an oxidation. So whatever is oxidized is the reducing agent. So make sure you're very comfortable with it. It's so easy that you have to get that point. You cannot lose that point, okay? So don't overanalyze it. We only do that because we're reviewing, yeah? Okay, so once you get the answer, then you just move on. So the answer is 1 plus, okay? All right, so I'm gonna just take a picture of this and then put it on our notes. So I was thinking that some of the easier questions, I don't wanna put into the notes. Yeah, let me just not put in the notes, yeah. Sometimes I'm just gonna do this, and then because it's gonna be video recorded, you can just watch it again if you have questions. It's easier that way, okay? So I'm gonna take away the drawing and move on to the next question, yeah? So the second one is stoichiometry. Every time you see molarity and volume, there's only one thing you can do with them, is to multiply them. Because every time you give them molarity and volume, they're trying to ask you for moles, yeah? So you want to multiply this. So this will give you the moles of S2O3, which is right here. So if you do this on calculator, you can multiply them divided by 1,000, or you can divide by 1,000 to get liter, then you multiply them. So it's your preference, yeah? So this is 0.1 times 0.5. So that's 0.05. Now, if I put 0.05, you are going to be wrong on sig fig. So it is not 0.05. 0.05 has only 1 sig fig. So if you look at this, you need to carry out to 3 sig fig here. Follow the molarity because there's 5 sig fig. You choose the smaller one. So you got to put 0.500 mole. Yeah, you can to show word. Okay. So that would be the S2O3, but that's not what they're looking for. They're looking for how many grams, right? So you just convert that into grams. So 1 mole into gram will be the molar mass. Again, your answer has to be 3 sig fig. So if you look at the scoring guide, okay, let me see where the scoring guide is. So here's the scoring guide. Okay, so if you look at the scoring guide, and you can see that here, you get 1 point, and your final answer is sig fig. Yeah, it's 3 sig fig. So you get 1 point for the number of moles. So you got to show word for that. That is showing word, and then you get 1 more point for the mass with consistent with the moles. Yeah, so you put the molar mass again. Don't round the molar mass. How do you get 158.1 from the periodic table that's provided? Do not round this to 158. Never round the molar mass. Okay. So just keep all the sig fig that you see on the periodic table, and that's it. So 3 sig fig question. Now, in this case, it doesn't mark you a point off for sig fig. Sometimes they do, sometimes they don't. So you never know. So you always carry out sig fig for the first 3 questions. Always. Yeah. Okay. Alrighty. Now, the next one here is that we're given this. Student use this solution. Now, if you look at these solutions, these compounds may kind of look confusing, but these are just your reactants. These are your reactants, right? So if you look at the reactants, again, the reaction is on the top. So you have 3 reactants, the S2O3, the OCl minus, and OH minus. Yeah, those are the reactants. So they're giving you molarity and volume for your reactants. Why would they give you molarity and volume? Again, the only reason is to find moles. Every time you have molarity and volume, you have moles. That's it. It's that simple, right? So they're trying to tell you the moles. And do you see they have an equal number of moles? Because the molarity and volume is the same. So if I have equal number of moles, who is the limiting? That's what the question is saying. Okay, and you have to justify, which means calculation or description, to justify your answer, which is limiting, right? So you need to look at the coefficient. Okay, to find the limiting, you just divide your coefficient. So if I have equal number of moles and you look at my coefficient, I have 1, I have 4, and I have 2. So if you have equal number of moles, so we're on question number 1, okay? You divide your coefficient, whichever is smaller is limiting. So this would be the limiting reagent with the largest coefficient, yeah? So for example, if I have 4 moles of everything, I have 4 moles of sodium hypochlorite, I have 4 moles of sodium hydroxide, and I have 4 moles of this. Doesn't matter how many moles, they're equal. You divide your own coefficient. Whichever is smaller is limiting, yeah? Okay, so this would be the limiting, sodium hypochlorite. Your justification could be an actual calculation, or you can just explain which one is limiting. So here, you get 1 point, and you look at the scoring, you only get the point for the proper justification. So if you guess this correctly without the justification, you do not get that point. So they will combine the answer, because you can guess the answer, always with the justification. Sometimes they do that, okay? All right, so this is the limiting. Why? So you said given the equal number of moles, that's your interpretation of this. And then from the coefficients, right? That in the balance equation, this will be depleted first. So, but what they're trying to say without calculation is that when you have equal number of moles, or it doesn't have to be equal, okay? You can take the moles of every single reactant, you divide by your own coefficient. The smallest one is the one that will be depleted first, okay? That is another way to use words to describe limiting. So next time, if you don't have to use calculation, if you want to use words, that's what you said. You find the moles of each reactant, you divide by the coefficients from the balance equation. The one that gives you the smallest is the one that is limiting, the one that will be consumed first. That is another way to explain limiting, okay? So do that, all right? So that's 1 point here, okay? So starting next week, we'll start adding up the points. Right now, you can do that too. You can see how many points, okay? All right, next one. Here's a solution. So again, this is about the same, is the same solution. Yeah, you're mixing 3 solutions together, and you can see the temperature started from 20 and it went up. Yeah. So what is the final temperature here? So if you read this closely, this is between 33 and 32, right in the middle. Yeah. So between 33 and 32. So this is 32.5. So you got to round this to 3 sig fig. That is the final temperature. Your initial temperature is 20.0. So if you subtract them, you got to round this properly. So this would be 2.5 as is, right? Not 2.50, okay? When you subtract, you round to the least decimal point. Both of these are 1 decimal point, yeah? So you answer 2.5. That's the change in temperature, right? So this again is exothermic because somehow the 3 reagents mixed together causes heat to be released from the reactions. So the environment heats up. So this is exothermic, okay? Exothermic releasing heat, all right. So we're told this, and then let's see what they want. Okay, according to the graph, what is the change in temperature? Sorry, I subtracted wrong. I meant 12.5, yeah. So this would be 12.5. So 32.5 minus 20 is 12.5. So don't make mistake what I did, yeah. So that will be the change in temperature. That's it. 1 decimal point. You're done. 1 point. There's nothing else to do here. And then part E, so again, continuation with the same reaction. They try to use the same reaction for a bunch of questions, okay? So the question is, the mass of the solution. So the mass of the solution inside the calorimeter is this, okay? Calculate the magnitude of heat released to the reaction. Assume that the specific heat capacity for the reaction is 3.94 joules per gram per degree Celsius, and the calorimeter does not absorb heat. So this one, I do want to bring it to our notes. Yeah. Okay. So this is pretty easy. Just Q equal to MC delta T. So if you look at this one, usually the Q of the reaction, okay, when you mix solution together, is going to be Q of the solution plus Q of the calorimeter. Okay. So that's the full formula, okay? So the reaction releases heat. Who is absorbing heat? The solution is absorbing the heat of release plus the calorimeter. But here the question says to ignore the calorimeter because calorimeters are insulated and does not absorb heat, right? So calorimeter does not. So we are told that doesn't absorb heat. Because if it does, then you have to include this term. So now it becomes, the reaction becomes the mass of the solution, MC delta T, times specific capacity for the solution, times the change in temperature for the solution. That is the heat of the reaction. And this is why the first thing we're told is the mass of the solution. If you see that the mass of the solution is 15.21, 4 sig fig. So 15.21, here we go. So 15.21. Now, on the test, I put units in, okay? When I usually do this, I don't because it's distracting, yeah? And I got to put the specific capacity for the solution. I'm going to put the units in too. Do you see that they specifically said here for the total mixture is this? So don't use that for water. Sometimes they say, assume it's similar to water, then 4.2, right? But right now, no, it's 3.94. So, and the change in temperature is 15.21. So those are the numbers that I need to plug it in. So this is 3.94. And the reason I show unit is just to show work. So the grams will cancel. And then with 12. What was the change in temperature? It was 12.5. Yeah. And then I put degrees Celsius, just show work. So my final answer would be in joules. Yeah. And how many sig fig? Well, not 4, right? This would be 3 because of the temperature, yeah? Now, technically, your specific heat, this is not a measurement, so forget about using that. Your only measurement is change in temperature and the mass given. So the specific capacity is considered constant, so that is not part of the sig fig, okay? So it's gonna be 3 sig fig question, and that's the answer, yeah? Okay, so from here, you can see the answer is this, okay? So 749. Do you have to give it in joules? No, you can convert that to kilojoules, just be consistent. And there's only 1 point. That's it, okay? Next one, using a balanced equation. So since I was writing balanced equation for the redox reaction, right? Calculate the enthalpy change, okay? So Q and delta H is not the same. They're related. And the equation I gave you between Q and delta H, let me go back to Q is 749 already. So this one here is 749. That is the answer. Yeah. I would always box the answer because whoever grade your paper is a person, is a teacher. I don't know why would anybody sign up for grading this. So you want to be as precise as possible, box your answer, yeah, so that he knows where you're at, okay? So the next one is to find delta H for the reaction, the one I gave you was this. It is plus, minus, because you indicate endo exo. And you put Q of the reaction you found, and you got to divide it by moles or limiting. That is how you find delta H for the reaction, okay, guys? So this is one of the 5 ways to find delta H that I gave you. Okay? There are 5 ways. So one is calorimetry. This is the formula. Second one is Hess's law. Next one is using heat of formation. Next one is using bond dissociation energy. And next one is from thermodynamics. There are 5 ways that the question can play around about delta H, okay? So we'll review those 5 ways, but this is for calorimetry. What is Q of the reaction is right here, up here. So this is also the formula I gave you for Q of the reaction. If you are thinking about calorimetry, if the question is about calorimetry, use this one. And almost always, they will say the calorimeter is negligible, it does not absorb any heat, so you just ended up with this, yeah? But if they do include the calorimeter, then you have to include the capacity, heat capacity for the calorimeter, okay? So that's the difference. Alrighty, so how do I do this then? Well, we do have the moles of limiting, don't we, right? So you go back to the equation, and we know the moles of limiting, which was sodium hypochlorite, right? And this is why they give you this information here. Sodium hypochlorite was our limiting, and we have 0.5 molar and 5 mil. That's it. 5 mil. This is not liter, so be careful. So 0.5 molar, 5 mil. I'm going to transfer that to our notes. Our limiting from previous was sodium hypochlorite. We have 0.500 molar and I have 5.00 mil. I have moles of limiting, okay, right there. And I also have Q of the reaction, which is from previous. And I want to do that in kilojoules because we are told to get the final answer in kilojoules per mole of the reaction. Okay, so if we do this, then our delta H for the reaction is plus minus, and 749 joules is 0.749 kilojoules. And most of the reaction you can calculate on the side and transfer over, or you can calculate right beneath it if you want. So to show work, if I don't have to show work, I just multiply 0.5 molar and 5 mils divided by 1,000 on calculator. If I choose to show work, then it's kind of annoying. So I put 0.00500 liter and I multiply by 0.500 moles per liter. So this is molarity times volume. So if I want to show work, that's what I would put there. And then I will return a final answer. Delta H for the reaction would be that, okay? Whatever that is. So let's see what we got. So we got 0.749 divided by that, okay? Let me just use the answer key, yeah? So if you look at the answer key here, that's what you'll get, yeah? Okay, so you'll get 1.2. Okay, so actually you'll get something different first. Okay, let me just do it out. I want to explain the difference here. So let me just do it out. My calculator is hard to key this in. Give me a sec. All right. Okay, so our calculator got, and I have to put negative, right? So it's exothermic, so negative 299.6 kilojoules per mole. Now, how come this is not the answer? Yeah, because if you look at the answer here, this is per mole of sodium hypochlorite, okay? It is not per mole of the reaction. Okay, so there is a difference. So let me come back to this in just a sec. So we talked about this problem with giving delta H. So let's look at this one more time, okay? If I use this to show you that 2A plus B gives you 3C, and the delta H for the reaction, I'm going to put, let's say, 600 kilojoules, and here I put per mole of the reaction, okay? There's always per mole of reaction. But this is for the entire reaction. What this means is that if you have 2 moles of A, it will require 1 mole of B to produce 3 moles of C, and it will require 600 kilojoules needed. And why is it needed? Because it's endo. I put positive here, right? But this is also true. This is also 300 kilojoules per mole of A, because 2 moles of A require 600. Wouldn't that be 300 per mole of A? And it's also equally true, 200 kilojoules per moles of C, right? because 3 moles of C produce 600. Wouldn't be 200 per moles of C. And this is also true, 600 kilojoules per mole of B. So there's a bunch of ambiguity. So AP decided to always report per mole of reaction. Yeah, this is always implied per mole of reaction. Not per moles of A or B or C. It is always per mole of reaction. Even they don't write it. What we got here is per mole of reactant. This is not per mole of reaction yet. And if you recall the reaction itself, I know I didn't copy and paste it, okay, but it's here, okay? If you look at the per mole of reaction, I'm going to take a picture of the reaction all the way up here. So let me take a picture quickly, and we'll put it in, yeah? So do you see the reaction here is actually 4 moles of NaOCO. That is bleach, by the way. Hypochlorite is bleach, yeah? So let me go back to our notes. So this is for 4 moles of this sodium hypochlorite. It's a strong base. It's very basic because the conjugate base of a weak acid, right? So this is basic, okay? So you see this is per mole of that right here, and the coefficient is 4. So you actually have to multiply this by 4 to get per mole of the reaction, yeah? Per mole of reaction will be 4 times, because this is for 1 mole, and one reaction has 4 times the limiting. So I got to times by 4. So times by 4, and I got to round to 3 sig fig. So that's why it's negative 1200, yeah, or 1.20 times 10 to the 3, yeah. So this is why if you look at the answer now, okay, for what we just did, they give you the final answer right here, yeah, okay. So this answer here is the final answer. What we did is per mole first and then adjusted for this, yeah, okay. They did a little bit different way, but the final answer is negative 1200, yeah? And put into scientific notation, because technically, if you put negative 1200, this is wrong, because the sig fig is messed up. That is 2 sig fig. Your answer should be 3 sig fig. So if you need to put those exact numbers, put into scientific notation, yeah? Okay, but this is the final answer. So look how many points this is. Number 1, identifying the limiting. Okay, and number 2, knows that 4-to-1 ratio must be adjusted for. And then number 3 for this equation, yeah? So again, this Q for the reaction divided by moles of limiting. But your moles of limiting is not moles of the reaction, so that's why there's a difference of 4, okay? So there's different way to represent this. So let me come back to this again, our notes here. So the example that I was using this A, B, and C. So if you look at this one again, if I know moles of A, how do I find moles of reaction? If the moles of A is 300, it takes 2 moles of A for 1 mole of reaction. Don't I have to times by 2? So that's why the moles of reaction is 600, okay? So please watch out for this. So delta H is ambiguous, so what does AP do? AP always reports moles of the reaction. Unless they specify A, B, and C, you always assume it's for the entire reaction, okay? So then there's no more ambiguity, okay? All right, let's look at the next one. So far it's not too bad. Let's see what else they want to play here. So now the student repeats the experiment. So this time, instead of using 5 mil, you see that they double the volume. So that means the moles is also double, right? Before it was 5 mil, now it's 10 mil. So I'm going to be doubling those moles. So if I double the moles, if we use common sense here, okay, this is part F, okay? So let's come back here. So this is again question number 1, part F. If the moles of limiting doubles, wouldn't that doubled amount of heat released? Would that make sense, right? Because you have twice the limiting, wouldn't you release twice amount of heat, right? Okay, and if you look at the heat of the reaction, Q of the reaction is mass times C times delta T. If the Q of the reaction doubled, you did not change mass, Mass is the same. It's still the same. Sorry, the mass also doubled. No, the mass changed. We did change the mass. I'm sorry, because we use different volumes, right? Okay, let me okay. So let me just skip this one. Okay, let's go to the delta H. So does delta H change? Yeah. Now delta H actually remain the same, because if you double the amount of heat, you also doubled the moles of limiting. So that ratio canceled out. So delta H will not change. Okay, the moles of limiting doubled because you twice the volume. The Q doubled, and the delta H still remained the same. Because since delta H is a ratio, yeah, you did release twice as many moles heat, kilojoules, but you also use twice as many moles. So that's what the question is trying to do, I think. Okay, let's look at what they want. So the question is that when we do that, the magnitude of delta H, okay, is the same. They want you to explain. So they tell you that delta H does not change. So why wouldn't it change, right? So basically what we just said, that doubling the volume, double the moles of limiting, okay? And since delta H is the moles, is how much kilojoules is released per how many moles of limiting, when you double both, the ratio, which is delta H, remain constant, yeah? That's just one point. So you don't have to write the whole paragraph, yeah? So that is the reason, okay? All right? All right. And then next one is the last one, I think. We have F. Write the balanced net-on equation. Oh, yeah. So this one requires you to know what? Your solubility rule, right? Because if you don't know which one is soluble, you guess. And you don't have to know too much solubility rule. All you have to know is all alkali ions are soluble. So you break them apart and you just write everything else. So if you look at part F, I take the molecular equation and I just have to dissociate whatever I can. Okay, you never break apart liquid like water. Can't. You just can't break it. Okay, so what do I break apart here? If this is for AP, I don't do the intermediate stage. Yeah. So for example, there's 2 sodium. I just write sodium, and here is S2O3 2 minus. So I break it apart. And here is sodium hypochlorite. Well, sodium is just sodium. I don't care how many sodium. And this is hypochlorite. And here again, sodium hydroxide. I just break it apart and hydroxide. You see this side again is silly sodium again is everywhere. Spectate ion doesn't do anything. That's why we cancel them out. I got sulfate. And here again, I have sodium, I have chloride, and water. You cannot break apart water. So you can see that you just got rid of a whole bunch of useless sodium ions. And on the test, I don't even show this, but I just want to show this right now. So all this is gone. You just have whatever is oxidized and reduced, because that's the major players. And then OH minus. And then here you have sulfate. And here you have chloride and you have water. If you just leave it like this, you get no points. What is the reason, guys? This is not balanced. Yeah, even though this is right answer, but it's just bad. So how do I balance this? Well, you don't have to do the redox balancing by half reaction method. They're already balanced for you. So the proper way to do this, guys, remember on the test, you just put 2 here for 2 sodium. This is 4 sodium, is 4 sodium, right? And this is 4 Cl. Now, and this one here is 2 sodium and 2 hydroxide. And here is 4 sodium total to cancel, right? And 2 sulfates here. And this is 4 sodium and 4 chloride. And this is 1 water. So if you were to carry out those coefficients, it is already balanced for you. So there's no work on your part. It is already balanced. You just have to carry them out, yeah? So if you decided not to do this intermediate step, know how to find them. So my eyes, when I do this, I just focus on this. I got 4 OCl minus, 2 OH minus, 2 SO4, 4 Cl minus, and water. That's all I do on the test. Does it make sense? Okay, so this is the balanced net-on equation, yeah? All right, so that's easy, 1 point there. Okay, let's move on to the next question. So that's question number 1. Okay, let's look at the next question. So we're done with this. So remember, you have 20-some minutes to do this. There should be plenty of time. So you want to do this. Like first question was pretty easy. You want to do as fast as you can. Maybe you only took 10 minutes. Then you save like like more than 10 minutes to do harder one, okay? All right, let's look at this one. So this one, the student investigates the reaction between nitric oxide. Okay, nitrogen oxides are bad. They're any kind of NXOY. These are smog. They're environmental pollutants. This is why we use the catalytic converter to get rid of them, so they don't pollute our environment. Yeah, like NO is a free radical. Remember, every time you see NO, you think about exception to Lewis structure. Nitrogen only have a 7 valence electron, right? NO2, bad. All these are horrible, horrible gases. Okay, but if you see NO, you should know NO is an exception to Lewis structure. This is a radical. It can grab electron and oxidize your DNA. That's not good. So that's what this is. Okay, so these are bad. So what about these? Okay, so they're saying here we have an equal molar mixture. Now, first of all, what does that mean? Equal molar. That means equal molarity. Okay, not equal moles. Do not confuse that. Equal molar means molarity is the same. If they want equal moles, they'll say equal molar and equal volume. Yeah, then the moles are the same. Yeah, equal molar just means same molarity. That's it. That does not mean equal moles. Okay, so anyway, that's a fine detail. And then what else? So the student produces using the reaction represented above. Okay, so what is above? Right here. So this is the reaction here. So do you see that this reaction is also redox? But they already played redox, so they don't have to do that redox anymore. This is that free radical one. This is O2, and this is NO2. So this is also redox reaction, okay? Oxygen is 0, oxygen is 2 minus, so oxygen is reduced, and NO is oxidized, yeah? So this is also redox, bunch of redox reactions. And they're all gases. This is not equilibrium, so forget about equilibrium, okay? So they wanted to draw this, number 2. So the particle representation, okay? What does it say here? The particle representation of the equal molar mixture shows the reaction between them, right? So the question is, draw reactant mixture of NO2. Draw them, reactant, is not shown here, yeah? That will yield the product. So they want to produce these products, draw the reactants. What would that look like? Okay, now I need okay, so let's look at this one and you zoom out a little bit. So if you look at the products here, you can just find out what the reactants are. So all you have to do is count. So for example, nitrogen is shaded. So there's 1, 2, 3, 4, 5, 6, 7, 8. There's 8 nitrogen after. So wouldn't there be 8 nitrogen in the reactant? Okay. And then oxygen. Well, oxygen is the rest, right? So there's 1. Okay, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So the 12 oxygen atom, they must be accounted for. So how do I draw 8 nitrogen atom, 12 oxygen atom using my reactant? And again, your reactant is NO and O2, right? So how many, so you gotta have NO. So this would be nitrogen and this would be oxygen. And there gotta be O2, right? Like that. So how do I draw that? Yeah. So wouldn't I draw 8 because I have 8 nitrogen, right? And then this would be 2 of those, right? Okay, like that. So this will produce, you'll produce this completely, right? Okay. So when you draw this one though, but you gotta watch out for how to draw them. So let's see if there's any other condition here. Let's just look at this. You just have to make sure they're balanced, right? Okay. So this one here, yeah. Because here, if you look at this, there's also another thing about this, yeah. So actually, let me take back. I thought this is what we're gonna draw, but this is not this is not all the same. So I'm gonna do a limiting before, change, and after for this one. For example, I'm just gonna do this here. 2NO plus O2 produces 2NO2. So before, change, and after. So here's after. I'm gonna keep track of how many NO2 I have. So there's 1 NO2, right? 2, 3, 4. So I have 4 NO2 after, right here. And I have NO. So how many NO do I have here? 1, 2, 3, 4. So I have 4 NO here. Yeah. Okay. So there's no more oxygen remaining. So oxygen is limiting, right? Okay. So if you look at the way this is set up, then you can come and look at the answer here. Okay. You draw out so that the both left side and right side must be the same. And if you look at this one, let me get rid of this. Clear? Okay, right here. Okay, so you see that there's 1, 2, 3, 4, 5, 6, 7, 8, and 2 oxygen, right? So I'm gonna draw that limiting thing again. Whoops, this is NO. And O2, this is 2 NO2 right here. So before, change, and after, right? Okay, so you have 4 of those, NO2, 1, 2, 3, 4, and then you have 4 of those, there's no more, right? And in the beginning, didn't we say we have 8, right? And we have no reactants, right? And so if you have 8 here, don't you have to minus 4 in order to get 4? Don't you have to plus 4 here, right? What about oxygen? Oxygen, if you look at the ratio, is 2 to 1. So this is 2 to 1, so you got a minus 2 here. And because there's no more left, you got to start with 2 here, yeah? So you can do a before, change, and after, showing you how much of each molecule you have before and how much you have left. So again, I have 4 NO2 at the end of the reaction. I have 4 NO at the end of the reaction. That's what they're saying here. I have 4 NO2 and 4 NO. There's no oxygen. So I use that diagram and I came up with this. Yeah. And I know initial, okay, I need 8, right? Nitrogen, and I said I need how many? Was it 12? Oxygen, right? But they must be in the form of NO and O2, right? So this would be 8 of this because you have to have 8 nitrogen. And how much oxygen? It has to be 2 because that's what's left over, right? You need 4 more oxygen, so left over is 2. So, but you can look at the ratio. That also makes sense. So you have to minus 4 here to have 4 left, and you have to plus 4 here because the ratio is 2 to 2. So to get 4 here, and you have to minus 2 for oxygen because the ratio says 2 to 1. And so that means without any oxygen remaining, you must have plus 2. So whether you use common sense to get the answer right here or using stoichiometry, both will give you the same answer. Yeah. Okay. So this is kind of like stoichiometry without numbers. Okay. So what if I do this, guys? Sometimes they will trick you, like they'll put 2 more oxygen here. That means oxygen is excess. You have 1 left. So that means you got to have 3 oxygen here. Okay. So because you're not supposed to have oxygen. Yeah. Because all of them here is either NO or NO2. There's no oxygen. But if you are given an oxygen remaining as excess, then you know it has to be here. Yeah. Okay. So sometimes they can do that. All right. So anyway, so this is pretty easy. I just overstudied it. I guess not a good idea. Okay, next one here. So here says that now there's another reaction. So this is not the same reaction. They said NO will react with NO2 to produce N2O3. And we're given these thermodynamic data. So when you're given thermodynamic data, right away you look at the delta H, delta S, and delta G. So first thing popped to mind is this is exothermic because H is negative. And it creates less disorder because S is negative as well. And when G is positive, the reaction is not spontaneous. Yeah. So then we look at those questions. Yeah. So if we go back to this, okay, when we do these kind of questions, we just have the 4 scenario for delta G, delta H, and delta S. So this is not it. Okay. This is lagging, so let me get rid of this. Yikes. Okay, so this one is what I want. Okay, let me put it over here. Okay, So remember, when we look at thermodynamic stuff, there's only 4 scenarios. This is scenario number 4, when both H and S is negative. Delta G tells us spontaneity. Delta H, exo endo. And minus T delta S, more disorder or less disorder. So right now, we have negative, we have an exothermic reaction that produces less disorder. So this is scenario number 4, okay? So in this case, G is positive. This is spontaneous at low temperature only, yeah, for this scenario, okay? But right now, the temperature is not low enough, so your delta G is positive. When delta G is positive, the reaction is said to be non-spontaneous, yeah? So you got the delta G for this reaction, you know this reaction is not spontaneous, okay? At this temperature. If you lower the temperature, it will be spontaneous, yeah? So that's the scenarios that we discussed. The other scenario, we also discussed is scenario number 3, when they're both positive. If they're both positive, then the driving force is delta S, the disorder. And in this case, you'll be spontaneous at higher temperature, because at high temperature, G is negative, yeah? Okay, so this scenario is easier to think about. So when temperature is hot enough, you're spontaneous. Like the example I use here is melting of ice. So if you look at the melting of ice will melt. This is an endothermic process. And when ice melts, the process also produces more disorder. So is melting of ice spontaneous? The answer is depends on temperature. If the temperature is greater than 0 degrees Celsius, the melting point, then yes, it is spontaneous. G will be negative. If the temperature is less than 0 degrees Celsius, too cold, then ice will not melt spontaneously, right? So it's the same concept here for this one when both are negative. When both are negative, you are only spontaneous when temperature is low enough. Okay, right now you're non-spontaneous because temperature is too high, right? So that's what we're told here. Okay, and every time you know delta G, you can find equilibrium constant. Delta G is negative RT ln K. If you know G, you always know equilibrium constant. One, if you know one, you know the other. It is the same information, yeah? So from here, I can plug in delta G 0.87, and it's in kilojoules. So I plug in negative R. R is 8.314, but that is in joules. So I divide by 1,000. So now it's in kilojoules. Temperature is 298. By default, those little zeros are 298 Kelvin. And then I can solve for equilibrium constant. If you do this stepwise, this would be a 2 sig fig question because 0.87 has 2 sig fig. So I'm going to divide everything over and see what we get here. Give me a sec. Okay, so you can do this on calculator and solve for K. So 0.87 divided by 0.008314, okay, and divided by 298, and it's negative. So this is negative 0.35. It's natural log of K, yeah? So to find equilibrium constant would be e to the negative 0.35, okay? So e to this power. And give me a sec. Okay, so negative 0.35 and e. Yikes. Okay, okay, this calculator is hard to use. Okay, so e. So I got 2 sig fig, 0.70, yeah? So do you see this is less than 1? So it's not spontaneous, right? So that will be your calculation to show what equilibrium constant is. So if you go back to the question asks you, part 1, calculate the value for equilibrium constant. Every time you have G, you can find out what K is, yeah? So they solved mathematically, and then they plug it in. Doesn't matter how you do it. It's only 1 point. Even if you mess up the sig fig, it depends on the grader. Technically, if you mess up the sig fig, they can mark you off. So always watch out for sig fig. This is 2 sig fig question. So there's 1 point. Giving you G, you can find K, Equilibrium constant. If you know K, you can find G always. Yeah. So that's the next one. Let's look at next one. Next one is that if both pressure, so this little p means pressure. Now remember, these are your reactants, okay? We're given this reaction that NO, NO2, these are the reactants. We're initially at 1, okay? They're initially at 1. Will the product pressure be 1 at equilibrium or not? Okay? So how do we know this, right? So if you look at if you look at the reaction will give you a clue, okay? And the spontaneity will give you a clue, right? So your equilibrium constant, so this one has to do with the definition of what is equilibrium. See, the answer is no here, okay? Because your equilibrium constant is quite small, okay? This means that reaction does not go to completion. Rather, you reach equilibrium. So this is equilibrium one. And what does that mean when equilibrium constant is less than 1? It's when your product over reactant, right? Your pressure for N2O3 over the pressure for NO and pressure for NO2. This is how you write the equilibrium constant expression. If it's less than 1, the reaction favors the reactant, okay? And if you assume this is limiting incorrectly, and this is what happens, okay? Let's go back to the equation. Let me take down the equation and put on the, right here. So if you see the equation, right? This is the equation that we are looking at, okay? So I'm going to transfer this over. The coefficient is all 1, 1, 1, okay? So if I put this on our notes here, okay? This one here, the equation essentially is NO plus NO2. All these are gases, produced N2O3. And we know that the equilibrium constant is 0.70. So equilibrium favors the left. Now, if I incorrectly assume this is limiting, so they say initially this is 1, 1, 0. If I incorrectly assume this is limiting, don't I have to minus 1, plus 1, right? So this would only be 1 if reaction goes to completion. And when reaction goes to completion, equilibrium constant will be huge. Every single reaction that goes to completion assumes equilibrium constant is like infinity. Because when you do products over reactant, there's no more reactant, right? So K is a ratio of products over reactant. So every reaction that goes to completion will have a huge, basically infinite value for equilibrium constant. And this is only 1 when you go to completion. And this reaction does not go to completion as indicated by the equilibrium constant. Since equilibrium constant is small and less than 1, the reaction does not go to completion. Yeah, does not goes to completion. So what does that mean? So that means that the pressure. So the pressure for N2O3 can never be 1. It's only 1 if you go to completion. So it must be less than 1. It's only a fraction of the reactant. So maybe instead of 1, it's like minus 0.1 or minus 0.02. A fraction of it reacts. Okay. So that is basically the reason. So this is equilibrium concept. So instead of having you calculate a nice box here, they want you to be able to put that in words. So look, the way they will say this, again, this is how many points here. This is just 1 point for justification, right? So once again, you said that this would only equal to 1 if you go to completion, and I would actually add both, right? Since K is less than 1, that means there's a bunch of reactants will be present, right? So I would combine them instead of just either or, but they're very linear, yeah? So on this one. So no, it does not go to completion. So the pressure is not going to equal to 1. Next one. This is Le Chatelier principle, yeah? If you increase temperature, okay, equilibrium always shift to the endothermic side. This is basic Le Chatelier, okay? If you increase temperature, Le Chatelier principle says equilibrium will do the opposite. So what is opposite of increasing temperature is to absorb them, to get rid of the heat, okay? So Now we go back to this equation. Okay, this is why we're given the delta G, delta H, and delta S right here. Okay, so you can see that the reaction is exo as written. So that means to the right is exothermic. So if you shift to the left, will be endo. So if you increase temperature, Le Chatelier predicts that equilibrium will do the opposite. If you increase temperature by adding heat, equilibrium will shift always to the endo side. And in this example, the endo is left. So equilibrium will shift to the left. Okay, so it's going to shift to the left. And if you shift to the left, you see that N2O3 will go down. And the other two, NO2 will go up, NO will also go up in concentration, in pressure, right? Okay, so this is understanding of Le Chatelier principle. So let's look at what the question wants again. Okay. The question wants you to determine right here. Okay, if you increase the temperature, okay, will the student says increasing temperature will increase N2O3, and that will be wrong, right? Okay, you disagree. Because N2O3 is the product. If you increase temperature, that will shift equilibrium to the endo side, which is the left side. And that means N2O3 will go down, not up. So indicate whether you agree or disagree. So right away, disagree. And then said that the reaction is exo. And then just regurgitate Le Chatelier. Increase temperature, you shift to the endo, which is left. And that will decrease N2O3 instead of increasing. So 1 point is bundled with the justification, yeah? Okay. All right, so that's not too bad, okay? So Le Chatelier principle. So to very quickly talk about Le Chatelier principle again, okay? If I have this NO gas, okay, let me ask you guys a few questions on Le Chatelier. And this is our equilibrium. I have this is N2O3 gas, okay? So, and the delta H was negative, okay, like that. So again, this is two gases becomes one. So left side has greater pressure. If you shift to the left, pressure will increase. If you shift to the right, pressure will decrease. Okay, and left is endo because as written, right is exo. Delta H is negative always as if you go into the right. So right is exo, left must be endo. So these are the rubrics. If you add stuff, equilibrium will always shift to the other side. So if I were to add NO, equilibrium will shift to the right side, to the other side of NO. So it doesn't matter what you add, okay? If you remove stuff, you'll always shift to the same side. So that's one of the stress. If you remove something, you shift to the same side, okay? The same side as you remove. If I take away the product, I take it away, I remove it, equilibrium will shift to the right, the product side. To produce more, it's always trying to do the opposite of what I'm doing, yeah? So that's what Le Chatelier is based on, okay? Second one is if you increase pressure by compress. So you compress the entire system by decreased volume, by compression. That is how you increase pressure. Then how do you do the opposite of increasing pressure? Do you want to shift to the side with more gas or less gas, right? Common sense would be less gas because you want to do the opposite, right? So by increasing the pressure of the entire system by compressing, the equilibrium will shift to the side with lesser gas. So the less gas side, yeah? Less gas side has less pressure. So this one should be written as a less gas side, which is the right side. So if you shift the right side, N2O3 will increase, okay? And of course, if you decrease pressure, you shift to the more gas side, okay? Now temperature is what we talked about. If you increase temperature, equilibrium always shift to the endo. If you decrease temperature, how do you do the opposite? You have to shift to the exo side to raise the temperature back up. That's how you memorize them, okay? So you never memorize left and right. Always memorize the rubric. And what does not shift the equilibrium? If you add a catalyst, does not shift equilibrium. If you add anything solids and liquid, does not shift equilibrium. If you increase the pressure the wrong way by adding noble gases instead of compress the volume, you're not going to shift. You can add a bunch of noble gases to the system, there is no shift in equilibrium. So no Le Chatelier principle. So this is usually tested. They'll throw something in like this. Now, only temperature can change the value for equilibrium constant, okay? When you do adding, removing, you change pressure or change the volume, equilibrium constant remains the same value. Even if you shift left and right, K does not have to change. Mathematically, that is possible. You can change the concentration of reactants. Since it's a ratio, they can cancel each other. Your K never changes unless you change temperature. Only changing temperature changes equilibrium constant's value, yeah? So it's very important, yeah? So I could have a follow-up question to what we just did, right? So what we did was you increase temperature. We said that here you increase temperature, you shift to the endo side, which is left. If you shift to the left, your equilibrium constant will decrease in value because you have less products formation and you're changing temperature. So equilibrium constant will no longer be 0.7. Okay, this is before. Since you shift to the left by increasing temperature, your equilibrium constant will drop from 0.7. Maybe it will drop to 10 to negative 3. This is after temperature increase. Yeah, it's going to be smaller. Okay, because you shift to the left, K will go down. Okay, so just keep that in mind. That could be a follow-up question on Le Chatelier principle. All right, next one. See, they continue with this. The gas that we produce, N2O3, now you can add water and you produce acid. This is nitrous acid. So great, you got a weak acid. So they want you to draw the Lewis structure for nitric acid. So remember, that's how you want to know how to draw Lewis structure. NO2 minus. If you add a proton, you get this acid, HNO2. It's basically H plus and NO2 minus. If you know how to draw NO2 minus, you get the answer. NO2 minus looks like this. It's bent. Nitrogen has 2 electrons. Everybody else is, so 2 lone pair. Yeah. So this is a bent. Nitrogen is 3 electron domain, right? Remember, double bond count as 1. Single bond count as 1, lone pair count as 1, is sp2 hybridized. And the molecular shape is bent. So if I want to add a proton here, where do I add it to, right? The proton is going to be added to one of the oxygens. And you want to pick the oxygen that has 1 minus oxidation state. I don't know what happened to my oxygen. Yeah, the electron disappeared. So here, this is 1 minus. Oxidation number is 1 minus on this oxygen. On the other oxygen is 0. So this is the oxygen. And 2 of those electrons from the oxygen will combine with the H plus to form nitric acid. That's how you draw the Lewis structure. So if I draw this again, this part has no change whatsoever. Okay, and this oxygen now has 2 lone pair because one of the lone pair is combined with proton, and that is the Lewis structure for nitrous acid. The nitrogen still remain the same hybridization. Okay, the hybridization here is still sp2 hybridized, and this oxygen is sp3 bent because that's 4 electron domain sp3 bent. Nitrogen is 3 electron domain sp2 bent. So what is the difference in the bond angle between sp2 bent and sp3 bent? sp2 bent, the bond angle is about 120, a little bit less than 120 degrees. sp3 bent, the bond angle is about 109.5, okay? So a little bit less than 109.5, like 105 if you want. So if they ask you for the bond angle, do not fall for the bond angle, guys, right? The bond angle about this nitrogen is 120, even though this bend is sp2 bend, but the bond angle for this oxygen right here is 109, is about 105. It's a little bit less than 109 because it's sp3. It's tetrahedral electron configuration. Yeah, sorry, electron geometry. So it's 4 electron domain, sp3 bend. So the bond angle is different. Okay. Now they did not ask for the bond angle, so I just want to point that out. Okay. So let's move on. So let's take a look at what's going on here. Right? So do you see that they're nice? They even give you the most of the Lewis structure. They just want you to complete it. Yeah? Okay? Well, this is the answer key, that's why. Okay, so I think they just put the atoms like this. They put it together. So I usually draw Lewis structure with lines. Don't draw dots, okay, guys? You you put dots in later. How do I know you need to use dots on lines? You look at the wording. If they say electron dot, then you put dot. Just replace the lines with dots. If they want the Lewis structure, then you just draw Lewis structure. Okay. Oh, and then furthermore, it doesn't matter here. It says line segment can be used, so always use line segment. Okay, don't use dot. Dot is stupid. Yeah, just use line segment. Okay, but this is what we drew. Do you have to draw them to the actual shape? No, which is great because drawing actual shape is more difficult, right? But they just want you to draw them. That's all. Okay. All right. That's it. 1 point for Lewis structure. So please know how to draw NO2 minus. Okay, it's bent. All right. So memorize it. Okay. That's the best way to do Lewis structure. Otherwise, you got to start with the rules. Add up the valence electron, draw single bond, fulfill octet, all that rules. And then what is the hybridization? Naturally, that's the next question. It's sp2. We already talked about it because the nitrogen has 3 electron domains. If you have 2 electron domain is sp, 3 electron domain is sp2, 4 electron domain is sp3, 5 is dsp3 or sp3d, and 6 is d2 sp3 hybridized. So it depends on the electron domain. One lone pair is 1 electron domain, single, double, triple, they all count as 1 electron domain. Okay. Next one. Next one is continuation. This is acid and base. Yeah, this is a titration now. So you have a weak acid that the student is going to titrate this with a strong base. So this is titration. When you have a titration, this is limiting. Titration is always limiting because anything strong, like the strong base, will react until something runs out. They're very dominating, they're not equilibrium processes. So this is titration, a weak acid titrated by a strong base. And you can see the net-on equation makes sense, right? The proton is basically got taken away by the strong base. Base want to take away proton. So the weak acid becomes conjugate base, right? Acid becomes conjugate base. A base becomes conjugate acid. That's how acid and base reaction often work, right? So conjugate acid has 1 extra proton than the conjugate base. So this is your titration, all right? So the student bubbles into water and then it becomes the weak acid. Great, so we start from here. That is the only species produced. So I got a bunch of this, all right? So your goal is to find out the concentration, the molarity of this. So why do we do titration? To find unknown concentration. That is one purpose for titration, yeah? So this one is a lot easier than it looks. So to read the titration, you have to understand equivalence point, yeah? So I did not talk about titration too much detail yet, but this is what the graph looks like. You can see that initially, this is the pH of the solution. So it must be acidic because initially I got a bunch of this weak acid, right? And you can see the x-axis is how many mils of OH minus added. And you can see from the graph, the more OH minus I add, the more basic the pH become. Okay, so you can see that the pH increases. However, it increases drastically about 20 mil. And this most vertical point of a titration graph is called the equivalence point. What does it mean by equivalence point? Equivalence point is defined to be the equal moles between the amount of acid that you have and the amount of the base that you add, okay? So if you add equal amount of acid and base, you have reached called the equivalence point, okay? So what this question essentially tells you is that you added 20 mil, because that's my equivalence point right here. I added 20 mils of the base, okay? That is 0.1 molar. I know it's 0.1 molar because we're told the base is 0.1 molar, okay? And you have 100 mils of this weak acid. What is the molarity? This is just stoichiometry. So this is not even difficult titration. They're just saying that if you added 20 mils of the hydroxide, that is 0.1 molar, and you have 100 mils of the acid right here. It's kind of hidden here, right? I have 100 mils of the sample, which is the acid here. Okay, and what would be the molarity, right? So this is just stoichiometry, and you get the answer. So how do you do stoichiometry? You can find moles. Moles of the hydroxide is moles of the acid is 1-to-1 ratio. If you know moles of the acid, you divide by 100 mil or 0.1 liter, then you have the molarity. That's it. Okay, so equivalence point is always the most vertical part of the titration. I can give you another titration that will look like this, and this would be the equivalence point. Yeah. So if it takes 20 mil to become the equivalence point, you divide 20 by 2. That is when you become half equivalent. So this is the half equivalence point. Okay, the equivalence point is the most vertical. The half equivalence point is whatever equivalent divided by 2. If this is 20, half equivalent is 10. If this is 30, half equivalent is 15. Okay, so half equivalence means you added half amount of base that is required instead of equal amount of the base. Yeah, so equivalence point is right here. Half equivalence here. Okay, so that's the titration. Okay, so how do you answer this question? It's stoichiometry. Okay, so if you look at the answer key, they just did a stoichiometry. That's all they will do. Yeah, here. Okay, so using the titration graph. Oops, sorry. Where is the what is the question here? Oh, okay. So the question is this one. This is the first question. Okay. So we want to use the titration graph to determine the initial concentration of this. Okay. So this is a little bit harder. If I were to take a picture of the titration, okay, we're gonna focus on the initial. Okay, so this is my titration. Let me take a picture of this. And then we'll go over more titration today. That is I wanted, titration is not easy. Yeah, so this titration. Okay. So if I come to the notes here, we said that when we deal with titration, okay, let's look at an example like this, okay? So this is just a little bit notes. Don't worry about finishing the test, yeah? So here's a note. Let's say I have 100 mil, okay, don't worry about citric for now, okay? This is a weak acid, okay, is titrated by and a strong base, okay? So this is 0.1 molar, okay? So I'm gonna say 0.1 molar, so the number is easy. It's titrated by, okay, 0.1 molar sodium hydroxide. Okay, this is my titration, okay? So this is a typical weak acid, strong base titration, and that's the graph we will see, okay? So by a strong base. So the question is, I want you to be able to find the pH at, okay, so A, when no sodium hydroxide is added. Okay, so when there's no sodium hydroxide. And question like this, they will have to give you the equilibrium constant. So the equilibrium constant is Ka, is going to be 10 to the negative 5 for my example. Okay, so that's the equilibrium constant. So how do you find the pH of this weak acid when you haven't started titration yet? That would be just icebox, because weak acid will dissociate partially. We don't dissociate weak acid completely. So weak acid dissociate a little bit. Look at the Ka is so tiny. You're gonna get few products at equilibrium only, right? So there's very little dissociation. So you gotta use the icebox to find it. So I would put 0.1 here, which come from that 0.1 molar. I don't care about the volume because icebox, initial change equilibrium, only takes molarity. Do not use moles, okay? So don't use moles. So don't convert this into mole. Icebox is molarity. Equilibrium questions are always molarities, yeah, here. If it's limiting, you use moles. So that's why I call BCA, yeah. BCA, I use moles. BCA, do not use molarity. So this is limiting, you use moles. If it's equilibrium, you use molarity for icebox, yeah. So that's the difference between those two. So I just put 0, 0. You cannot minus 0.1 because that would assume 100% dissociation. That is not the nature of a weak acid. So you minus X plus X plus X. And I got 0.1 minus X, right? So I can use the definition of equilibrium constant to solve for X. I just do products minus reactant, right? So this would be X squared over 0.1 minus X. We've done this multiple times. right? You do products over reactant, and to avoid quadratic, you just drop off minus x. Otherwise, you got to use quadratic, right? So you always drop off plus or minus x's to avoid quadratic. So now I can solve for x easily. I cross multiply. X squared is 10 to the negative 6. So that means x is 10 to the negative 3 molar. And what is x? X is hydrogen concentration. If I have hydrogen concentration, I can find pH, which is negative log of hydrogen concentration. I will get 3, yeah? Don't worry about sig fig for now, yeah? So that will be the pH when no sodium hydroxide is added, okay? So if I were to turn this into a titration graph, where am I on the titration graph? I will be right in the beginning of the titration, yeah? So this is the pH. And remember the titration graph kind of look like this, right? Okay, you got the most vertical region, that's the equivalence point. And this is the moles of OH minus added. So I am right here. I have not started titration yet. This is point A. I just found the pH here is equal to 3. So this is maybe pH 3 right here, okay? So then what about if I continue to add? What if I add, let's say, 30 mil? So part B, what if 30 milliliters, 0.1 molar sodium hydroxide is added, okay? I start over again. I have 100 mil, 0.1 molar weak acid. I added 30 mil. The question is find the pH, yeah? Okay. So how do I do that? So now you have a titration. This would be limiting. Every time you add a strong base to weak acid, limiting what happens. And your reaction is this one. Don't worry about sodium. You just put OH minus. And this is non-equilibrium. Limiting is BCA. Okay. So your weak acid is now titrated by the strong base. The base will grab away the proton to form water, and you're going to get A minus. And to do these kind of questions, you got to use BCA. You have to use moles. So I transfer the information here. I have, for example, 30 mil, and I have 0.1 molar of the strong base. And I have 100 mil of the 0.1 molar weak acid, okay? So I transfer them over so I can do moles, right? This is the question again. I have 100 mil, 0.1 molar of the weak acid. I added 30 mil, 0.1 molar sodium hydroxide. So how do I convert them to mole? You just times them. So 100 mil, do you see that molarity is moles over liter? But molarity is also millimoles over milliliter. So I can just use millimoles if I want to. I just multiply 30 millimol without changing to liters. I times by 0.1. 30 times 0.1 is 3 millimoles. I don't have to use moles. If I use moles, 3 millimoles is simply 0.003 moles, right? So I use 3 millimoles. What about, so this is not 3 millimoles, wrong place. 3 millimoles is the hydroxide, right? 30 times 0.1 is 3 millimoles. What about the weak acid? Is 100 times 0.1, that's 10. So you added 3 millimoles to 10, okay? So before there's 0, 0, right? So limiting, this is limiting, this is not equilibrium, so you minus 3 plus 3. We don't care about water. So you have 3 and 7 remaining, okay? So I have base and I have acid. What kind of solution is this now? Do I have a buffer solution? The answer is yes. Remember last week, we said that a solution with both acid and base is a buffer. I have a buffer because I have A minus, I also have HA. Buffer is when both are present. And I give you the formula to calculate a buffer solution. The pH of buffer is the pKa of the acid plus log of A minus over HA. So we know what the Ka is, 10 to the negative 5. So pKa means negative log of that, which is 5. Okay, again, P means negative log. So this is pKa becomes 5. Okay, And then you plug in log of A minus over HA. A minus is 3, HA is 7. That is the pH of the buffer. If you keep this in the calculator, you will have 3 over 7 log, and then plus 5. So I got 4.6. Okay, about 4.6. Okay, so after adding 30 mil, I am now at 4.6 for pH. Initial pH, remember, was 3. Okay, I don't know what happened here. pH was 3 initially. So we found out the half equivalence point would be 50 mil, and the equivalence point would be 100 mil. And this is 4.3 after 30 mil. 1, 2, 3, 4, 5. So 30 mil, the pH is at 4.6. Is it 4.6? Yeah, 4.6. Okay, before it was at 3. Yeah? So if you continue to do this at every single point of the titration, you will plot this thing. Yeah. Okay, that's why this is the titration graph. So again, the most vertical region is called the equivalence point, and half of that would be half the equivalence point. How do I know 100 mil is required to become equivalent? You look at the definition of the equivalence point. Moles of the acid must be moles of the base. So you could use this definition to find it. So at every single equivalent point, because moles of acid have to equal to the moles of the base. Yeah. Again, my acid is HA right here. So you could do this also. You can do molarity of the acid times volume of the acid, that is moles, must equal to molarity of the base times volume of the base. So this is MAVA times MBVB. And you also adjust for number of protons that the acid have. Some acid have 1 proton, some have 2. You also adjust for the number of hydroxide. That's what this IB is. Some base have 1 hydroxide, like sodium hydroxide. Some base carry 2 hydroxide. So if you recall, my acid is HA, so there's only 1. My molarity was 0.1. I have 100 mils. My sodium, I'm using sodium hydroxide, so IB is 1. Molarity of the base is also 0.1, so I solve for VB. So the volume of the base requires 100 mil. 100 mil is needed to reach equivalence point. That is how I know that it will take 100 mil to reach the most vertical part of the titration graph. It will take 100 mil because of the definition of equivalence point. If I divide 100 mil by 2, I will get 50 mil, and that would be the half equivalence point. So when I added 30 mil, I know I am right here. I have not yet reached the half equivalence point. So I'm almost there. If I add 50 mils, I will be half equivalence. If I add 100 mils, I will be fully equivalence point. So to plot the titration graph, we have to find the pH at every single point of the titration. Okay. So for example, the next one is going to be a half equivalence point. So part C, I will add 50 mil, 1 molar sodium hydroxide. Okay. Again, this is to 100 mil, 0.1 molar of this weak acid. Okay. This is half equivalence point. I know that because I did the equivalence calculation. I knew 50 mil is going to be a half equivalence point. So look at how to find the pH here. So you do the same step. Whenever you have a titration, you have to take care of the limiting. And the limiting is always the same equation. You write down your weak acid, you put the OH minus, and the weak acid will become the A minus because the proton will be grabbed away. You do BCA first. So essentially, whenever you do this, you always do BCA step 1 because that's limiting. And then step 2, you do the buffer equation or icebox. Okay, there's always 2 steps. So I like to transfer the information. Once again, I have 50 mil, 0.1 molar, that is 5 millimole. Again, I'm using millimole because the numbers are small. I have 100 mil of the 0.1 molar unknown acid, and that is 10 millimole. 0, 0. Limiting, so I'm minus 5 plus 5. So you can see that after adding enough to become half equivalence point, this is what I have left. I found out that the amount of acid and conjugate base is equal. And I am still a buffer because a buffer is a solution that has both HA and A minus. So the second step, I can use the buffer equation to find the pH. Is again pKa plus log, put the base on the top, conjugate acid on the bottom. And look what happens. You have 5 over 5 because the A minus is 5 millimoles. The HA is also 5 millimoles. And this is true at half equivalence point. You will always have equal amounts of A minus and HA, which means log of 1 becomes 0, and your pH is always equal to pKa. This is a fact that this is always the case at half equivalence point. Because at half equivalence point, your amount of HA equals to A minus at half equivalence point. And log of 1 will always drop out. The pH is pKa. So when I plug it in, pKa is negative log 1 times 10 to the negative 5, which is 5. So my pH is equal to 5. So after 3 points, I started with 3. After 30 mils, I have 4.6. After 50 mil, I am at 5. So do you see? That's why it starts to level off, okay? And you continue to do this, you get a titration graph. So let's look at that titration graph from a different perspective right here, okay? So this is now without numbers. And if you look at this kind of titration graph, this is pH, and you know you have to add a base because that's why the pH increases. So I want to be able to label this for any kind of titration, yeah? The initial point of the titration is HA. That is the initial part. Okay? And at the equivalence point, all you have is A minus left. All the HA is converted into A minus. At half equivalence point, we said earlier, the amount of HA must equal to the amount of A minus, always. That is why pH equal to pKa. This is true at every half equivalence point, yeah? So half equivalence point is a very important point of the titration. This is true. pH is always equal to pKa because the moles of acid and base conjugates are equal. And at the equivalence point, all you have is A minus. So what if I'm in between? If I'm between here, then the amount of HA will be greater than A minus. If I pass the half equivalence point, then the amount of acid is less than the conjugate base, yeah, in terms of quantity. Okay, and when I'm at the equivalence point, I have A minus left. What if I'm beyond equivalence point? What is in the solution? I will have A minus and bunch of OH minuses because I'm adding OH minus beyond the equivalence point. So I'll be adding a bunch of OH minuses. So I need you to know these points of the titration. Again, initially, all you have is weak acid. You haven't started the titration yet. At the equivalence point, all you have is A minus left. All the acid becomes conjugate base. Half equivalence, you're halfway there. So the amount of acid and conjugate base will have to equal. And that is exactly what we have shown here. You see that this is before, this is half equivalence. So do you see the amount of acid is 5, the amount of conjugate base is 5. So after you added the base, you have 5, 5, indicating right here, the amount of acid is equal to the conjugate base. That's why the pH is equal to pKa. And if you are before the equivalence point, like 30 mil, remember our 50, this was 30, your HA is greater. And it is. If you look at this one, my HA is 7. Which is greater than the amount of A minus conjugate base. It's not 5.5, it's 7.3 because I have not yet reached half equivalence. My acid must be greater, okay? So that's what we are saying here. Like this is 7 and this is 3, okay? If you pass the equivalence, your HA is less than A minus, and if you add equivalence, all you have is A minus. And if you beyond equivalence, you will have accumulated OH minuses because you keep adding them. Okay, so you have to understand this conceptually. This entire solution, as you add base to it, will look like this. This is the burette. Whenever you deal with titration, you need to use burette because it is the most accurate instrument to transfer specific volumes. Yeah, it is graduated, so you can see how much you're adding, transferring. So this particular question, guys, we are doing a titration. So in here, I have 100 mil and I have 0.1 molar HA. Yeah, I know the concentration. Yeah. So I have a bunch of HA in here, and then what am I doing? I'm adding OH minus, right? So I'm adding, this is sodium hydroxide. I have 0.1 molar, and I'm adding this. And we calculate this, it will take us 100 mil to become equivalent. So as I add them, I am plotting the pH. So if I add a 30 mil, I find the pH, I plot it here. And I start over again. Then I add 50 mil, and the pH becomes 5. And I start over again, I add 70 mil, 80 mil, 100 mil, until I have 100 mil. And then I go beyond 100 mil. I go beyond equivalence, 110, 120. This is the graph that will produce, yeah? So this is called the titration graph. There are 3 types of titration. This is the second one, okay? So that's what we get here. So make sure you know when to use a burette, okay, to transfer accurately, and this is titration. Now, look what happens now when I'm adding to the equivalence point. I'm fast forward to equivalence point. So at equivalence point, I have to add 100 mil, 0.1 molar sodium hydroxide, okay, to 100 mil, 0.1 molar HA. So I'm at equivalence point. Now the methodology is identical. You still have to do step 1, which is limiting BCA. You gotta use moles. And then step 2, you use icebox, or if you have a buffer, you can use the buffer equation. Yeah, if you're not a buffer, you have to use icebox. Okay. So the first step is always limiting. The second step is equilibrium. Always, for every titration, you have to do the limiting first. How do I write the equation for limiting? We've been writing them. I don't care about sodium. I just care about the weak acid reacting with the hydroxide. Sodium is useless, spectator. And again, we've been writing this BCA. This is like the 3rd or 4th time we're writing this, right? And I use a template, HA. It doesn't matter what kind of acid. So it's going to grab away the H from the weak acid to form water and A minus, yeah? And then I transfer the information. Now I have 100 mil. Okay. There's 100 mil, 0.1 molar HA. I also have 100 mil, 0.1 molar hydroxide. I added 100 mil into 100 mil. So total volume is 200 mil now. If I use millimole, this would be 10 and 10. Do you see this is the definition of equivalence? You added equal moles of acid and base, 10 and 10. And look what happens after the reaction is completed. You minus 10, plus 10. You see, after that, you have only A minus remain. Isn't this what we said? That after you have A minus left on this titration graph right here, you have A minus left after the limiting. After the base has been reacted completely, all you have left is A minus. So we're at the equivalence point because we're adding 100 mil. Now, that's it for the first step. Now, there's no more weak acid. So solution now, unfortunately, is not buffer. So you cannot use this buffer equation. This equation only works when you have both HA and A minus. If one of them is 0, try to plug it in. You cannot plug in 0 here. It's not going to work because it's not a buffer. This equation does not work. So you have to use icebox. There's no choice. Okay, there's no other way to do it. So if I were to use icebox, this is a weak base. How do I do a base icebox? I have to use equilibrium constant KB. Our K is 10 to the negative 5, so KB must be 10 to the negative 9. Why? Because they multiply. Conjugate equilibrium constant they multiply to 10 to the negative 14, right? Ka times Kb must equal to 10 to the negative 14 if the conjugate. So I have to use the base because that's what I have. I have a weak base left. So how do I write a base icebox? You write the base, you have to add water. We wrote down the icebox before. This equilibrium is controlled by Kb. Base will happily accept a proton and water becomes OH minus. That is the icebox. This is not BCA, this is icebox, this is equilibrium, this has to be molarity. You have to now put in molarity. You cannot put in moles. Okay, this must be molarity. So how do I find molarity? This 10 is not molarity. This 10 is millimoles. So to put into icebox, I have to convert 10 millimoles into molarity. I just divide it by the total volume. The total volume is 200 milliliters because I added 100 and 100. So this is the molarity. You see, millimoles over milliliter is molarity. 10 millimoles divided by 200 milliliters. You see the milli just cancels. You have moles per liter. That is the molarity, 10 over 100. And I do icebox with this. Initially, there's none. Because it's icebox, I minus x. I don't know how much dissociate, right? So this would be x and x. And this is 10 over 200 minus x. And I use Kb instead of Ka to solve. Kb is 1 times 10 to the negative 9. This is x squared over 10 over 200. Again, you drop off the minus x. So solving for x allows you to find the hydroxide. So x is now hydroxide because it's a base. So if I solve for x on the calculator, it will be 10 over 200 times 10 to the negative 9 times 10 over 200. All right. So I take a square root. So the hydroxide is 7.1, 10 to the negative 6 molar. So I can find out the POH, negative log of this, is 5.2. And then I can find pH, subtract from 14. So 8.8. So that is the pH at equivalence point. So I can go to my pH graph and put that point 8.8 in. So this graph is at equivalence point, the pH will be up at 8.8. Okay, we just found it. And all I have left is A minus. Okay. And if I keep adding, the pH will go up quickly because I'm adding more hydroxide along with a bunch of weak bases. So that is how you find the pH at every single point. So that is a titration. And what does that have to do with this question we just did? Okay. If you look at the question we just did, we're asking to find out the initial concentration of this. Given not much information, given this, the pH, right? You see the pH is about 2.5, between 3 and 2, right? About 2.5. Okay. So how do I know what the initial concentration is, right? Okay. You can look at the graph to do it, or you can look at this because they gave you we know how many moles we have. So this one, you have to remember the question. Okay. Well, let me just go to the answer because they tell you how many moles you have. Right here. Yeah. Okay. So they use the definition of equivalence point. Okay. So let me let me just transfer this over. I think I already took a, yeah, I already did this. Yeah, let's do this. Okay, let me put on this one. So I'm going back and forth, but please understand titration. Whenever you do titration, you got to do those two steps. BCA, because anything strong, yikes. Let me go back. Okay, anything strong will react to completion. So you have to do BCA, which is limiting, gotta be moles. And then depending on what's left, if you have a buffer, use buffer equation. If you don't, you have to use icebox, that's it. And there's only 2 icebox, one for weak acid, one for weak base. So here was the question. The question is a little bit different. We have a weak acid here, but the question here is that we don't know what the molarity of the weak acid is. We are told there's 100 mil. And this weak acid is HNO2. So that's what I have right here. I have HNO2. This is my equivalence point. All I have is going to be NO2 minus. And the half equivalence point will be half of 20, which means here, my HNO2 in moles will be same as NO2 minus in moles. The pH will be equal to pKa. Yeah, half equivalence point. So this question wants us to find out what is the molarity of this. So I use the definitional equivalence point. Because the base that we add, we know the molarity, we know the volume. So equivalence point, IB, IA, MA, VA must be IB, MB, VB. If you say it really fast, it's like amaba, ababa, like that. So, but remember this, yeah. Your IA is 1, there's 1 proton. Potassium hydroxide, IB is 1, so it doesn't matter, they cancel out. Molarity of the acid, that's what you're looking for. You have 100 mil. Molarity of the base is 0.1 molar. And volume of the base needed to reach equivalence point, they want you to be able to read that, 20. And then that is the answer for molarity of the acid. So this one here will be, so basically 1/5 of this, right? So if you do that, it will be 0.1, basically divided by 5. That's 0.020, yeah? So I'm not following the sig fig, but the answer is 0.020. But look how they do it. It's the same, yeah? So how do they get 0.020 down at the bottom? They're saying that this is how much base needed to become equivalent. This is the sodium hydroxide needed to become equivalent. This is from the chart. And this is the molarity. So they know you have to add this number of moles, and moles of the base must be the moles of the acid at the equivalence point. And since you're 100 mil, you have 0.1 liter. Moles of the acid, volume of the acid is the molarity of the acid. It's the same thing. This is exactly the same as IMAVA, IBMBBB, yeah? Because molarity of the acid, volume of the acid, that's moles of the acid. That is the moles of sodium hydroxide. They must be equal at the equivalence point, okay? So you get 1 point just for that, understanding the definition of the equivalence, okay? Now, how do you find the pKa? That is the half equivalence. For every titration, the pH is the pKa at half equivalence. So they want you to be able to read off the chart and estimate. You read the chart and you estimate the pKa is about 3.4. So pH is equal to pKa right at half equivalence. Right? How do you know the half equivalence? Equivalence and divide by 2. So you gotta be able to extrapolate and read this part right here, yeah? And it's about 3.5. I would have put 3.5, okay? But anyway, that's what that is, yeah? Okay, so any titration, doesn't matter if it's a weak acid, strong base, strong acid, weak base, the pH is always pKa. Now, if you know the pKa, you can actually find equilibrium constant. Because P means negative log of Ka is 3.4. Multiply negative inverse, so it's 10 to the negative 3.4. That would be the equilibrium constant. You just found the equilibrium constant of this acid. Okay, so using the formula, pH is equal to pKa, and that is always the case at half equivalent. So please remember that. You hear me say it over and over again. Now, next one, part F. During the titration, we added only 15 mil, right? So where am I in this titration graph? Have I reached the equivalence point yet, or half equivalence point, right? Remember our equivalence point was 20 mil, half is 10. I'm adding 15, so I am somewhere here. So I am between the half equivalence and the equivalence point of the titration. So if I am halfway there, at half equivalence point, I know my acid and the conjugate base must be equal, and at equivalence point, I only have conjugate base. So somewhere 15 mil, which one is greater? Is that the acid or the base will be the conjugate base? Yeah, so that's why the answer is NO2 minus. So the question is, during the titration, after 15 mil of the base is added, which species, the acid or the conjugate base, is in higher concentration? Because 15 mil is between half equivalence and equivalence, the conjugate base is higher. if I added, let's say 7 mil, then I will be before the half equivalence point. Then my acid will be greater in concentration. Yeah. So it just depends which point of the titration. Yeah. So how do they say this? The titration is past half equivalent. Yeah. Half equivalent is 10 mil. Therefore, more conjugate base. That's all you have to say. That is the justification. Yeah. Okay. So there's the titration. All right. So no more titration. Now, since we're looking at the titration, I want to go over, acid and base. I want to go over one more, which has to do with acid and base. I think this question is, we're not going to be able to do the electrochem yet. This one is, what is this one? This is also kind of like acid and base, okay? So that's electrochem. We're going to do that soon. So here, this is also acid and base equilibrium, okay? So if you look at this, isn't this icebox? Icebox, that's the weak acid, and you see the equilibrium, right? So you can write acid icebox, just break them apart. This is the cheating shortcut. Yeah, the proper way is to add water, and water will accept a proton from the acid. That's why you get H3O plus and you get F minus. So this is the proper way to write the icebox. Okay, H3O plus functionally is identical to H plus. There's no difference. It is basically water with H plus added. So it's like H plus writing on water. So for acid icebox, there's two ways to write it. You can just break apart the acid. That's the shortcut. But the proper way on AP, they always want to add water to it. For base, you only have one way to write the base, KB. Base will accept a proton and become HB plus, and water becomes OH minus. So this is the base icebox. All right. So this will be it. So the question is now, the ionization dissociation of weak acid is represented. They give you the concentration and it says the percent ionization is 13%. So what that means, guys, is that you can do the icebox now. Okay. And the 13% tells you what X is in the icebox. 13% of that dissociate. 13% of 0.035 dissociate. So if I take a picture of this, okay, this would be my dissociation. Yeah. Okay. So let's picture. Okay, here we go. So this tells you everything you need to know about the icebox already. So if I show this in my notes here, okay, because we have to go back and forth so often, that's why I rather you guys just watch the video and go over it again and just fast forward the part that you need to review. So I'm gonna actually do the icebox here to show you what that means. Yeah. So your equation again is HF plus water. This is the proper way, and this will dissociate according to Ka and becomes H3O plus and F minus. This is icebox. You have to use molarity for icebox. Usually when we do icebox, we put the molarity right here, which we have. So 0.035. We don't care about water. 0, 0. You would have to minus X plus X plus X, right? We were just doing that. But the 13% tells you exactly what X is. So X is the percent ionization. X is 13% of 0.035. So you can multiply it out. 13% of 0.035 dissociated. 5 times 0.13. That means X is 4.55 times 10 to the negative, okay, 4.55 times 10 to the negative 3 molar. So you just found out what X is. If you know what X is, you can find the pH is negative log of 4.55 times 10 to the negative 3. Yeah. So you already know what the pH of this solution already. So, and you also can find out the equilibrium constant. Look how much information you already have. Okay. How do I know the equilibrium constant? Because equilibrium constant is X squared, which you know what X is, divided by 0.035 minus X, right? So wouldn't that mean you can calculate the equilibrium constant? Equilibrium constant is just 4.55 10 to the negative 3 squared divided by 0.035 minus X. I don't need to approximate by dropping off x because I'm not solving for x. So if I do 4.55 10 to the negative 3, I'm going to square this and divide it by 0.035. So x is about 5.9 times 10 to the negative 4. That is your equilibrium constant. So you see that just with that little information, 13%, you found the pH. You also found the equilibrium constant for this weak acid. Okay, does that make sense? All right, so there's a lot of stuff. So what are we doing here? Okay, let's go back. So the question here is not about icebox there. So the question says, two particle representation of the ionization. Now remember, HF is weak. It's weak acid. Weak acid cannot dissociate completely. So the question is, water molecules are not shown. So you can see this is HF, this is F minus, and that is your H3O plus. So which one is more accurate? It tells you, yeah? Explain why figure 1 is better than figure 2, yeah? Okay, why is that? Because figure 2 shows 100% dissociation. That is not what weak acids do. And how do I know this is 100% dissociate? Because I don't see any more HF. It's gone. There, if you look at the diagram, there is no F minus. It's 100% dissociated. That's wrong. Where figure 1 is partial dissociation, right? Partial dissociation is what weak acids do. So I know this is partial because I got a bunch of HF remaining. You see this is HF? I have a bunch of them. I only have a F minus here, right? A bunch of them. And I have a H3O plus. So I have one dissociation. Everything else is not dissociated. So that's your explanation. Does that make sense? Okay, so there's no calculation here. They just want you to understand strong is figure 2, weak dissociate partially. So most of them will remain as HF. Yeah. Okay, and then part 2, we already did that. Use the percent ionization data to calculate Ka. And we know Ka was x squared over 0.035 minus x. And we said x is 13% of 0.035 molar. And then you just plug it in. Then you can solve for Ka. We did that already. All right? Okay. So don't worry about part C for now. Okay. Part C is a little bit more like conceptual. Okay. So, but let's just look at the answer. So we didn't get to do all the questions, which is okay. Yeah. We'll gradually speed up. And the answers are, again, they're online. So you can always check online for the answers. In case we don't finish them, yeah. The rest is we'll patch it up quickly, but I want to point one more thing out, okay? That you guys did this, the photo, the PES, photo emission spectrum. Remember this, PES? So it came back here again. Identify the element. Remember, the PES is electron configuration, right? So very quickly, you always start with the highest binding energy. This is 1s2. This next one is 2s2, and this is 2p3. This is nitrogen. Nitrogen is 1s2, 2s2, 2p3, right? So there's 2 electrons here, right? 1s. 1s is the most difficult to remove. That's why it has the highest binding energy. Always start with 1s. Then you have 2s and 2p3. So this is nitrogen. That's it. Identify it. Do you have to justify? No. Just identify. Just write down the answer. That's it. Okay. So towards the end, there's a lot of very easy questions. You don't want to waste your time, so you didn't get to them, right? And how do I know what the rate constant is? Half-life, rate constant. All radioactive decay is first order. All radioactive decay is first order. So it is 0.693 over rate constant. If you know the half-life is 10 minutes, you just divide by 10. So that is your rate constant. Unit is always 1 over time. Minutes, so it's 1 over minutes. Second is 1 over second. All radioactive decay is first order. All radioactive decay is, yeah? Okay, unless you're told otherwise assume it's first order. And then the next one, you don't even need formula to do this. Start with 64 atoms of the isotope. What is the amount? How much time will pass when you only have 1 left? So this 64 is a good number because you can divide by 2, divide by 2 again, divide by 2, divide by 2, divide by 2, divide by 2. Then you can count exactly how many 10 minutes pass. That's 1 10 minutes, 2, 3, 4, 5, 6. So it'll be 60 minutes. So you don't need to use the equation, this one. This is the first order integrated rate law. You could have just said, okay, I'm going to plug in natural log of 64. I want to become natural log of 1. And I just found my rate constant here. And you solve for t. You also get 60. So that is redundant. It's too hard. You only do that with the horrible numbers. But 64, they give you a slack. Yeah. So you could have just plug it in and you get a 60 minutes as well. So easy enough, right? So that towards the end, you see question like this, super easy. You have to get to them, okay? The biggest mistake is to leave them blank. There's no penalty whatsoever, either multiple choice or free response, okay? So there's one question we had to skip, and there's another question I didn't get to, so it's okay. We'll worry about the points a little bit later. But right now, our goal is to get comfortable with titration. It's very important we do titration. This question number 3 I didn't do, but they're pretty easy. Yeah. So you can look at the scoring guide. We'll get back to these kind of questions if you have time next week. Okay. All right. Then we'll stop here, guys. I'll see you guys next time. Thanks for coming in. Okay. All right.